All right, everyone. So we've got today Jeff Rosenbluth, who is going to be giving us an overview of the diagrams library. And it's great to have one of the core contributors here to tell us all about it. So take it away, Jeff.
Okay. Is the mic working? Great. So we're going to talk about the diagrams library, which Ryan mentioned. It's an embedded domain-specific language for making vector graphics. The embedded part means it's just a library in Haskell, and we write regular Haskell code, and we have the full power of Haskell at our fingertips to do what we want using the language. I'm going to spend a little bit of time trying to describe what we mean by declarative. That's a bit of a overloaded word these days. People usually mean it to talk about a language where we describe what we want the program to do, not so much how we're going to do it. In diagrams, I mean something actually quite a little bit different than that. Before I jump in, can I just see by a show of hands how many people have used the diagrams package at all? Okay, so very few. That's good because I don't presume any knowledge for the talk. So. Okay, so we're going to start our talk on diagrams by looking at a program in another language called Asymptote. Asymptote is a vector graphics language. It's written in C++. It's very powerful, and I don't want to take anything away from the Asymptote language by comparing it to diagrams. They call Asymptote descriptive as opposed to declarative. And I don't even really know how to program an asymptote, but what I wanted you to notice about this slide is that this function, which creates a picture, works by manipulating points in the 2D coordinate space. So if you look at this function, which I've renamed a function because I wanted you to guess what it does, is it just takes pairs of points and it manipulates them and it recurses based on calculations at the point level, and it draws its diagram by connecting those points. Does anybody use asymptote, or can anybody want to venture a guess at what this function does? So it actually creates a Sierpinski triangle. And if you just kind of glance back at the code, you can kind of see that the A is the kind of apex of the triangle, and it calculates where the points are of those triangles, and then it recurses. So again, the main point is that we're really manipulating points in 2D coordinate space. So here's the same program or the same function in diagrams. And I'm hoping, looking at the diagrams code, it kind of almost resembles the Sierpinski triangle. We look at the variable S, and S is just one level less deep of a Sierpinski triangle, and we recurse on that. And then we put it over itself, next to itself again, which is very much the kind of recursive flavor of the Sierpinski triangle. So the triple equal operator puts one diagram over another, and the triple bar operator puts one diagram next to each other. And this simple function generates a Sierpinski triangle. What's nice about the diagrams version is if I wanted to make a change, if I wanted to change the underlying element from, let's say, a triangle to a circle, or I wanted to change the fill color, that's actually quite easy to do. So in this one, I've made just a tiny few changes. I changed the fill color to orange. I changed triangles to circles. And instead of aligning the bottom two triangles, or in this case, circles, Sierpinski triangles, excuse me, on their center, I align them on the left, and I get a right triangle made with orange circles. Think back at the asymptote language and imagine how hard that would be, or what you'd actually have to do to make this function draw circles instead of triangles as its key element. And so the point is that when I say diagrams is a declarative language, what I really mean is we usually don't want to manipulate points when we're creating diagrams. We usually want to talk about where the diagrams go in relation to each other. And that kind of helps us make diagrams at a very high level and not so much worry about the coordinate space that they're in. It wouldn't be, I should also say that it's just one step away from kind of generalizing this to a function, a higher order function that takes, a shape, a color, and an alignment, and kind of makes any different type of Sierpinski triangle you wanted. So let me just talk for 1 second about what I'm not going to talk about in this talk, because the information is readily available on our website. I'm not going to tell you how to install diagrams, and I'm not going to describe the kind of module structure. The best place to find that out is on our site. We have an extensive user manual. We have many tutorials, including a Getting Started tutorial. If you've used Diagrams 1.2 and want to go to the latest release, which is 1.3, we have a migration guide on the changes that you need to make to your code. So please visit the website. It's got a tremendous amount of information. It's got a great gallery, and although we're not web designers, we put a lot of effort into it. Diagrams has been around for 4 years now, and we have 5 very active developers, including myself, and we're up to 67 contributors, so it's a great community. If anybody's interested in getting into some open source and learning a lot more Haskell, it's a great place to work. We advertised this talk. I said I would talk about some of the new features in 1.3, but I'm really going to gloss over those really quickly, because if you haven't used 1.2, they'll be very much lost on you. So one of the things we now have is projections. You can describe a diagram in 3 dimensions and then project it down into 2 dimensions, and like we did with that house at various angles. I should also say that Diagrams is an extremely flexible language. It has the ability to create 3D and 2D diagrams. I'm going to talk about 2D diagrams in this talk. We've added the ability to calculate where paths intersect, which is a fairly requested feature. We've added the ability to kind of change the opacity of a group of items, so you don't get that overlap that you see on the left if you describe the opacity of the combined diagram as light. And perhaps most importantly, we've added 3 new backends. So this is probably a good time to just say a little bit about the architecture of Diagrams. Diagrams has a pluggable backend system. So when you install Diagrams, you can install with it 1 or more backends. Each backend has different capabilities. These are all 2D backends, or we don't have any 3D backends that are supported yet, but we're working on them. And each backend does something a little bit differently, has some features and output capabilities that the others don't. So the PGF backend, PGF is kind of the parent language of TIC-Z. It's kind of like PGF is to TIC-Z as TeX is to LaTeX. So if you wanted to include a diagram in a paper or in a LaTeX document, the PGF backend would be your choice. Also new is the Canvas backend, which opens up a 2-way server, and it talks to a local host, so you can write interactive code, which diagrams that animate and diagrams that have buttons and a UI. And its sister, if you will, the Diagrams HTML5 backend, which actually just outputs raw static JavaScript. So let's just look at a somewhat complete diagrams program just to get started. We always have the no monomorphism restriction. If you don't, you're going to run into type errors that you're probably not going to know what they mean. So as a matter of course, for as long as I've been working on it, we've been just putting that language pragma on top. If you're using GHC 7.10, you're probably going to need the flexible contexts and possibly type families as well. So if the compiler asks for those, just give it to it. We almost always include Diagrams prelude. That's like the GHC prelude. It exports almost all of the API and all of the functions you need to make diagrams, and at least 1 backend. And there are lots of different ways to use the backends. The command line module for each backend allows you to create an executable that creates a diagram. So here I'm using the SVG backend. So when I compile my Haskell program, I get an executable that when I run it, takes some inputs that describe the size of the diagram and outputs an SVG file that you could load in your browser. The rasterific and the Cairo backend make PNG and animated GIF output. So different backends have different capabilities for what type of output they have. And they also have some of them have some special features, like Cairo has the ability to, has advanced text handling features that some of the other ones don't. The type of a diagram, in this case it's diagram B, which is an alias for a much longer type that I'm going to get to towards the end of the talk. The capital B is a little bit of a hack. It's something that's exported by each backend. And the way diagrams works is the backends don't have to render all of the diagram's primitives. They can render a subset or a superset of what's already included in the libraries. And the way we hook those things up is by exporting that token from the back end. That way the type checker can tell you if a primitive you're trying to use is implemented in your back end or not. So the type of a diagram, we include that token. The other thing I wanted to say about this slide is we use that hash sign for reverse function application. It's often convenient to say, okay, I have a circle of radius 1, and I want it to have an ultra-thick line width, a purple stroke, and an orange fill color. So we can use those to kind of chain together styles or transformations after on the back end of it. Lastly, the main width function is kind of the most common entry point into a diagram. So as I said, when I compile this, I get an executable that allows me to that takes as command line arguments the length and/or width, and will produce a diagram in that size. But main width is actually a lot more flexible than that. You can use it to create programs that take any number of command line arguments. You could specify the color and various things like that. There's a tutorial on using that, using the command line module, so I won't belabor it too much here. Okay, so part of the theme of diagrams being a declarative language is that we make diagrams by putting together other smaller diagrams. So once you understand how to compose diagrams, then you're really off to the races to kind of make whatever you want in the library. And there's some kind of slightly tricky things in the way diagrams are composed that I want to cover in kind of the meat of this first hour. So here's a diagram where I've got a small blue circle on top of an orange circle, and I just put those together using the atop operator. Atop is meant to be used infix, and you can think of a top as a top in kind of the Z direction, kind of out towards you. So it puts the blue circle on top of it. I've included behind it a little bit more idiomatic way we would write that. We would write that using the semigroup append operator. Almost everything in diagrams is a monoid, including diagrams themselves. So we typically would combine them using the mappend operator that you see there. I also wanted to include the actual atop operator because different objects in diagrams have different semigroup instances. So when we use the semigroup instance for diagrams themselves, it puts one on top of the other. If we would use it for paths, it would connect the two paths end to end. So we have a lot of polymorphism in diagrams. So sometimes you just have to be aware of what you're using what operator for. It's also pretty easy to put two diagrams next to each other, side by side. I use that kind of triple horizontal bar operator that we saw in the Sierpinski Triangle, and the triple equals puts one over the other. So how do these things work? So the key concept, in addition to a top, is that every diagram has a local origin, and that's origin with respect, let's say, to its own local vector space. So here you see these two circles have their own local origin, and when I put them together with a top, I match up the local origins. And so this is the same graph as before, only I'm showing the origin. Show origin is a helper function, a debugging function, if you will, that we have to show you exactly where the origin winds up. So how does that side-by-side operator work? Well, it actually is a combination of two things. It moves the origin, and then it calls the atop function. So if you look at the orange circle, originally the origin of that circle was right in its center. When I combine it with the blue circle using those 3 vertical lines, it does it in 2 steps. First, it moves the origin out to the left of the orange circle, and the amount it moves it is equal to the radius of the orange circle plus the radius of the blue circle. And then it combines those 2 things with the semigroup operator, with the top, and matches up those origins. And when you do that, you get exactly what we had before. You get this diagram. So the general function of which kind of those triple bars and the triple equals are special instances of is called beside. And what beside does is it takes a vector, in this case it's the vector 1, 1, and it aligns the 2 diagrams along that vector, in this case just so that their outsides are just touching. You can see I have a little bit of a funny syntax to describe that vector, the caret ampersand sign. That's what we use to put together 2 coordinates. It's also polymorphic. In diagrams, we make a distinction between points and vectors. So depending on what the code needs, that'll make either a point or a vector. In this case, it's making a vector. So there's a moral to this part of it, and the moral is we've got a ton of operations for composing diagrams, but they all can be implemented in terms of moving the origin and using the top command. So if you kind of understand the way that works, if you see some operator and you go to combine things and you don't necessarily get the result you want, thinking back to the fundamental fact that it's all about local origins and the top. So I've left out a little bit of a crucial fact. When I said that we put the orange circle next to the blue circle by moving the origin of the orange circle over, I didn't tell you how diagrams calculates how far to move it. In order to calculate how far to move that, we need really some concept of a boundary, right? Because I wanted to first move the origin to the boundary of the orange circle, and then I wanted to move it by the same distance the origin of the blue circle was to its boundary. That's how I get the origin where I want it. So in vector graphics languages, there's basically a couple of choices that you can make for your boundaries. In diagrams, we chose something called envelopes, which I'm going to describe in a minute. The more common boundary is probably bounding boxes, which just are kind of rectangles around it. Bounding boxes don't really suit our needs that well in diagrams, because if we try to combine those 2 circles along that 1, 1 vector using bounding boxes, and we arrange it so that the bounding boxes don't overlap, we would get something like this. And that's not the semantics we're looking for in diagrams. The bounding boxes come with kind of a whole host of other problems. If I rotate the diagram, what do I do with the bounding box? Do I rotate it? Do I not rotate it? Bounding boxes don't compose well. If I compose these 2 diagrams and then I have to draw the bounding box of the combined diagram, I get kind of a much bigger rectangle. Another alternative people might think of is actually the boundary or the path of the diagram itself, but that's actually quite complicated, and as I hope to explain in a bit, that won't really guarantee that you don't get overlap when we're putting diagrams together. So what is an envelope? So if you think of a diagram, as I said, as having a local origin, an envelope is a function that takes a diagram and a vector and returns the distance along that vector that you have to go until you hit the supporting hyperplane, or until you hit that red line. So it's thinking about it a little bit more intuitively. The picture really will tell it all. If I look at the circle, the envelope of the circle in the direction of the black arrow is how far I have to move in that direction till I hit a perpendicular line and the entire diagram is on one side of the line. You can see, looking at the pentagon, if you look at the top arrow in the pentagon, that the notion of perpendicular is actually crucial, because there are many lines that intersect at the boundary there, such that the pentagon is on the left side of the arrow. So it's the perpendicular line, and the last one actually gives you kind of an example that the envelope doesn't always agree with exactly where the boundary is, or the trace of the diagram. So in that case, the distance of the envelope takes that vector past the point of the right side of that pentagon, so that it keeps that rounded rect all on the left side of that line. And it's important to say, I was going to say it later, but envelopes are they're an intentional measure. In other words, they're not a boundary. It's a function that takes a diagram and a vector and returns a distance. So we don't store, an entire bounding box, or we don't store something akin to a convex hull. We just store this actually function, and they compose very nicely with things like max and whatnot. Okay. So here are those circles again, and here I'm actually showing what happened to compose those by calculating the envelope. I calculate the envelope in the direction of 1, 1 from the little circle, and that gives me a distance. And then I calculate the envelope in the opposite direction in the big circle, and that gives me another distance. And then I move the origin, that total distance from the big circle to the little circle, and that's where it has to go in order to combine these two diagrams so that they're just touching. Any questions about what I've said about envelopes so far? It could be a little bit confusing the first time you see it. Okay. So we could, if we would have combined two squares, we would also get what we think we should get intuitively. What I want to ask you is, what if we combine these two squares instead of using the vector x equals 1, y equals 1? What if we used 1 1/2, 1? In other words, if we made the slope a little bit more horizontal, if we used the line with a slope of 2/3, a half in the x, 1 in the y. It would slide down, but not touching. It would slide down by not touching, and that at first looks a little bit counterintuitive, and envelopes are somewhat counterintuitive, but let's draw in the separating hyperplane. And you can see why those two squares actually wind up where they do. And there's actually a good reason for that, because the envelope actually guarantees that no matter what the shape of the diagram is, that its entire substance is on is on one side of the hyperplane. So it guarantees that we don't have any overlap between the two diagrams, no matter what their shape, as long as we know their envelope. So that's what's going on. Yeah.
So is this an envelope for both shapes, or it's two envelopes that just happen to coincide?
So in order to align the diagrams, I need to calculate the envelope for each shape. And the envelope for each shape, what I do is, since an envelope is actually a number, it's a function that produces a number when I give it a vector. So in this case, I give it the vector 1 1/2, 1 on that lower left-hand square, and it tells me how far I have to move to its origin to get to that red line. And then when I do it for the above square, I use negative 1/2, negative 1 1/2, negative 1. I calculate the envelope in the other direction, so it goes to that line. Then I add together that total distance, and that's the amount I have to move the origin out of the top square in the direction of the lower square. So when I combine these with the top, I get the desired result. Now sometimes this is not the behavior you want, right? Sometimes you really want these things to be next to each other, and I'm going to show you how that can be achieved in a minute. But I just thought I would just say a few more words about envelopes before we leave the topic for a while. One is they're dependent on the local origin. Two is, I call them intentional, but they're actually extensional. I got those two confused, meaning they're not that red line. That red line is an intentional version of what an envelope would be. In other words, that the red outline in each of those is I calculate what the envelope is at each point around the circle, as I turn that vector around like a clock, and that's what happens when I draw the envelope. And if you think about it, or take out a pencil and paper and actually do it, these two graphs kind of make a lot of sense. It also highlights the fact that the envelope is not the same as the convex hull, right? The convex hull of a square is a square, so the envelope is actually quite different. And it's not too hard to convince yourself that if you did use the convex hull, you could get overlap. You could actually convince yourself using two squares as long as you rotate them in the right direction. And if you align them by where the convex hulls intersect, you will not get what you want. I've actually written up a little bit, just a little kind of almost paper, if you will. It's at that URL in our documentation if you want to kind of think about what the mathematics underlying envelopes are. It's interesting, in the early days of diagrams, I think Brent who started the project, might have been using bounding boxes, and in a kind of a blog post, somebody commented on it and gave him the idea for envelopes. And we've been using envelopes for 4 years, but I said, this has to be a mathematical thing. Somebody has to have thought of this idea before. And sure enough, it's pretty much what's called a support function in mathematics, which is it's a support function, but if you normalize the vector and calculate its support function, that's what an envelope is. And the details of it are in that paper, and it also shows it kind of proves that the envelope and the convex hull are not the same thing. Okay. So it's often convenient when, I'm sorry.
So the envelope is dependent on the geometry of an object and the center point that you choose?
Right, which I'm including as the definition because the object has a local origin. So I'm including that as part of the definition of the object.
Okay.
But if you want to think of it that way, you could think of it as a function of the center and a vector.
Okay. And what can you say, so the envelope always includes the convex hull, right?
Yes.
And
It's strictly greater than the convex hull. You can think of the convex hull as
that's if you have the center point within the object? Is that? I'm just trying to figure out
what does a convex hull even mean if the center point is not in the object?
I guess.
I think even if the center point is not in the object, the envelope will include the convex hull. One way to think of the convex hull in an extensional point is here we've kind of gone along that vector and we found a perpendicular line that encloses the diagram. The convex hull will allow you to use any slope. That's kind of an extensional thing about the convex hull. But if you look at that paper, hopefully it's pretty clear. Sometimes it's useful to move the local origin around to the border, to the envelope, before composing. We have a lot of these operators. We have beside, but sometimes you want and need to do things by hand, and sometimes you'll want to change the origin of a diagram to recompose it. You might want to have the origin on the left-hand boundary, compose it with one diagram, then move the origin to the right-hand boundary, and compose it with something on the other side. For that, we have a family of functions called align, and align moves, as I said, the origin to the boundary, where the boundary is defined as the envelope. So in this case, I have a bunch of hexagons, and what I really want to do here is make a honeycomb. So my first attempt, I use these align functions. If you look at the hexagon, on the left, I use the align R function. That's the align right function. That moves its origin to the right edge of the envelope. But if I look at the top right hexagon, I use the align bottom left function, and that moves its origin down to the bottom and then to its left. So actually that one red dot is the origin of all three of these hexagons. And so in this case, the corner of the envelope is not the same as the border of the diagram. So it doesn't really get you what you want. And you could see that because if you move the origin first left in the upper hexagon to the boundary, then you would have to draw the perpendicular right down from where it is, and that would kind of get you to a point outside of the graph. So align is exactly what you want if you want to align things by envelope, but that's not always what you want. Before I go on and show you what you do want, I want to mention one other idiosyncrasy of the code here that we do pretty often in diagrams. You see I have show origin with a tick mark at the end of it, or actually a single quote. And that's just like show origin, but it takes a record of default options. And if I want to modify that record of default options, here I'm using the lens operators. Almost all of our record APIs are basically lenses in diagrams. So in this case, I want to make the size of that origin a little bit bigger so you can see it. And we kind of pun a little bit on that word width. Width is kind of the default record, and then you can change it by using any one of the lens operators, or directly if you would. So in order to align these things in a honeycomb, we actually need another concept of a boundary. And that concept is probably more familiar to people. It's the concept of the trace. So the trace is like a little mini ray tracer. We have a diagram again, and that diagram has an origin. And this time we pick a vector, and we want to know how far we have to move along that vector to hit the border of before it escapes the diagram. Not every diagram has a trace. You can have open-ended diagrams, and not every diagram. I won't say that. That might not be true. So that's. We actually have a bunch of trace functions, because if you extend these arrows in your mind, you'll see that they intersect the objects in a bunch of different points. We can actually recover all those points. We can recover the max. We can recover the minimum of them. We can go in various directions. But for now, just think of it as hitting the point you would intuitively think. And the parallel function to the align function family of functions are the snug family of functions. The snug family of functions move the origin to their trace boundary, not to their envelope boundary. And you can see, for the most part, what I changed in the code was I changed the word align to the word snug. I have a comment there that asks, why not use snug bottom left? There actually is a function, snug bottom left. Can anybody answer what would happen if I used it? The problem with snug bottom left is it's dependent on the order. If you snug bottom first and then snug left, you're okay. But if you snug left first, you kind of get to that outer point, and then when you go to the bottom, you'll wind up exactly where you were in the envelope situation. So it's somewhat unclear what we even mean by BL, for snugging. Should it be in the -1 direction? It turns out that after putting together the slide presentation, I brought this up and we decided to deprecate it. So it's clear enough to use them separately, and we couldn't think of a good semantics for snug bottom left. But you can see here that when you use the snug functions instead of the align functions, you get exactly the honeycomb you want. So all these functions are contained in a module called align, or maybe it's alignable, and it's actually even more flexible than this. You could, if you wanted, define your own boundary. You could define it as a bounding circle, or whatever you wanted as your boundary, and it would be very easy to extend these functions to move the origin to that boundary instead of the ones here. So that's kind of what I want to say about composing diagrams, and I'm hoping that kind of help you understand when you put two diagrams together, or two paths together, or two trails together, any of the primitive things we have in diagrams. Hopefully that will kind of, when you're scratching your head, maybe you'll remember back here and understand if some of the results are not as intuitive as you thought. Okay, so I think we promised to use diagrams to kind of make some fun things. I don't want this talk to be kind of all about the kind of technicals of where origins are and how we calculate boundaries. So I thought we'd use diagrams to create a two-mirror kaleidoscope. So this is actually kind of a kaleidoscope-y-like thing that I created with the code I'm going to show you in a few minutes. If you I actually meant to bring in my kaleidoscope, but I forgot it. But I really liked playing with a kaleidoscope as a kid, and somehow I must have seen a picture of one on the internet and said, this would be really fun to build in diagrams. So I started doing it, and then I went on to Amazon.com and I bought a cheap kaleidoscope to see what the real ones are like. But it turns out if you kind of Google around and try to understand how a kaleidoscope works, the optics are actually quite complicated, because you have these mirrors, and in between the mirrors is this chamber where you put kind of somewhat random stuff, what I call confetti, but each kaleidoscope has its own, and then it kind of reflects up kind of infinitely. But if you look at the kind of 2D version, it's actually quite simple. You take the triangle, you take an isosceles triangle, and you just reflect it along one of its boundaries and compose it, and then you keep doing that until you go around the circle, and that's exactly what you get here. I think this is an isosceles triangle with, there are 12 of them in this circle here, so they're each, I guess, 30 degrees, and you just kind of flip it and rotate it and put them together, and you wind up with what I think is kind of a cool-looking picture. I will say that you need to have an even number of triangles, otherwise when you match up at the end, they will not, your kaleidoscope will look like it has a seam to it. Okay, so good. So preliminaries, my kaleidoscope is going to be random. When you have a real kaleidoscope, you turn it and the stuff falls around. But what we're going to do is we're going to generate just a bunch of random dots of random colors, random sizes, and random positions. And that's going to be kind of the confetti we put in our chamber. So most of this is kind of plumbing for the random numbers, 3 of these modules or 2 of these modules, control.monad.random and system.random. This just allows us to kind of hide the standard random number generator, kind of much like hiding state in the state monad. We hide the generator. Those other 2 functions just kind of specify the ranges, the size value for the size of the radius or the size of the pieces of confetti I'm going to be using, and the coordinate value, all the x coordinates and the y coordinates going to go between -5 and 5. So what I'm calling what you put in the chamber confetti, and we're generating it here. There's nothing really magical about this function. I just kind of generate, kind of big lists of those random numbers, and then I kind of put them together with zipping. So first I zip together the x and y coordinates using a function called makeP2 that takes 2 numbers and makes a point out of it. And then I use this make circle function that I designed above, which is just going to make a circle of radius s. It's going to fill it with a random color, and it's going to give it a random opacity. And I'm going to take off the line width so that it doesn't have all these black lines around it. I should have mentioned that there's one other package here that you might be interested in. It's called the palette. It defines a lot of ways to pick really kind of interesting colors. So the module I'm using is web colors. You pass it somewhere between 0 to 330 or something, and it gives you one of the HTML5 colors, but they're in kind of a random order, so hopefully if you put them next to each other, there'll be a decent amount of contrast. If you've ever looked at the Brewer set of colors that are kind of commonly used in D3 for map drawing of things, those are also included in that library. And kind of a harmony package, which allows you to kind of pick one color and a color theme and kind of generate several other colors that will go well with it. Something like Adobe Cooler, if you've ever looked at it. So when we build the confetti with that, we give the algorithm, we just choose a random seed of 0. We pick 50 pieces of confetti, and we get something like that. And just really easy. I'm just, eval ran kind of takes the random number generator out of the monad. I have to pass this in a random number generator, and I get the confetti. So next thing I want to do is cut a triangle out of this confetti. Another approach would have been to kind of build a triangle first and then kind of put random things in there and make it look interesting. But it turns out when something kind of gets cut off on the border of the triangle and then we do the reflection, it kind of looks nice and interesting. So I wanted to do it this way. So the next step is to cut out a triangle. And the way we do that is we need to create an isosceles triangle. We have lots of different functions in diagrams for creating polygons. We have a triangle function for creating an equilateral triangle, but if you want to create a isosceles triangle, you need to use the polygon function itself, or at least that's one way to do it. I included the type of isosceles here to kind of highlight one thing that I've been hiding from you a little bit. The almost nothing that you've seen type is kind of set in stone. So when we saw circle 1 and square 1 before, I set those types to be diagrams, but those are actually very polymorphic. Those have types very much like isosceles here. There's something that we call trail-like. Trail-like is anything that can be made out of a trail of points and a local origin. I don't want to get too deeply into that because it can take up a whole talk in itself, but most of these things, most of our functions and diagrams are polymorphic, and usually they just do what you want. So in this case, by writing the type signature as this kind of more general one, or leaving out the type signature completely, I'm going to get what I want from my isosceles triangle, which is what I want as a clipping path. I don't want a diagram, I want a clipping path, and that's of type path. So I write that in the more general way, and I use the polygon function, and you can see kind of that same idiom I've used before with the, before I called it width, but here I call it depth for defaults. They're synonyms in diagrams. and I use the lens operators to kind of set the features of the polygon and do a little trigonometry on the back of an envelope to figure out how I have to turn things around, and I get the triangle I need for the clipping path. Then I define this function make triangle, which is going to take an integer, which is how many triangles I'm going to cut my circle into. It's going to take a diagram, which is going to be my confetti, and it's going to cut a triangle out of it. And the way it does that is by using the clipped function. So clip takes a clipping path. In this case, I define that to be the triangle, and I apply that to, first I take my diagram, I make sure it has no line width, and then I clip it. Diagrams actually has at least 3 clipping functions. There's clipped. Well, I guess what I should say is the difference is what is the envelope of the end result. So if I clip the confetti in this case, what should the envelope be? Should it be the envelope of the clipping path? Should it be the envelope of the confetti? Or should it be the, some sense, minimal envelope of the two things? The clipped function chooses the envelope to be the envelope of the clipping path. There's also clip to and clip by for the other two things. Okay, so once we do this and we make our triangle, and it's cut out, which is exactly what we want. And now all we really have to do is kind of flip that triangle along, rotate it about, if you will, one of its sides, and recombine it. So when we do that along the left side, we get that. I put the black lines of there just to kind of show you exactly what's going on, and that they're actually 2 triangles. And if we do it one more time, then the pattern becomes clear what what needs to be done. So I keep flipping a triangle. I calculate what I have to do to put it in the right place. I put it in the right place, and if I go all the way around, I wind up with filling the whole space I'd be looking through in the kaleidoscope. So here's the code that kind of does that. We just need one helper function, which I call iterate index, which is just like the diagram's iterate function. It applies a function to an initial object and then keeps iteratively applying that function and generates an infinite list of that function applied n times. I need something a little bit different here because I want to be able to pass an integer in, because depending on which triangle it is in the list, I'm going to act on it a little bit differently in terms of its rotation. So there's nothing magical about that. It's just a slight generalization of the iterate function. There might even already be a diagrams function that does it. I just couldn't find it. And then once I have that, I'm pretty much done, because I just make my triangles by building my confetti. I cut them out with the make triangle function, and then I reflect them. About a vector starting at 0, 0. And created using this point I calculate from this function here, which probably needs a tiny bit of explanation. I'm not going to explain the geometry, but what I will say is, in addition to points and vectors, we have a concept of directions in diagrams. A direction is very much like a vector, but it's forgotten its magnitude, so to speak. And xdir is kind of the x-axis direction in the forward direction. So if I rotate that by an angle and then pass that with the origin to the reflect about function, I'm going to get the proper reflection of the triangle about one of its sides. And the whole iterate index thing is so that the next triangle gets rotated around the proper size. Okay. So once we do that and we apply that, then we concatenate these. We concatenate all these diagrams using the mconcat, which is the monoidal concat function. It's just like I could easily have just kind of put a top in between all of them if I knew how many there were, and we wind up with the full diagram. So here it is with 6 triangles. And here it is with 10 triangles, and so kind of pretty easy to make and kind of fun. So how is this kaleidoscope different to the kind of toy I bought on Amazon.com? Well, on Amazon's kaleidoscope, everything is kind of moving around. The confetti is in this kind of fluid inside the chamber, and gravity is kind of pulling it down. and everything's moving in front of you, giving you kind of really kind of a cool look. You don't have that here. You've got kind of a static diagram. But it's actually a trivial change to this code to add a few lines that create a frame-by-frame movement of that confetti, and then you can kind of put it together in an animated GIF, and it looks really cool, kind of almost mesmerizing. In fact, I'll show you what that looks like in the second half of the talk. But as a benefit, I get to kind of make this, put whatever kind of things in the chamber I want, put as many pieces I want, change it out, different colors, black and white, if you will, and gives me a whole lot of flexibility and a lot of kind of fun playing around. If you Google enough, you can find like a whole cottage industry of people who really make kaleidoscopes, kind of positioning mirrors, and they taper them and they angle them, and they get kind of really cool stuff. And I think a lot of them, from what I've looking at, they don't really have a clue what it's going to look like until they build it, and then they see what it is, and then they kind of do the math afterwards, and they analyze it, and they say, oh, that's kind of cool. But you could kind of do it here and kind of test it and see exactly what it's going to look like kind of pretty easily. So I think this is probably a good spot to take a break. Before I do that, let me tell you what I'm going to talk about in the second half and see if there are any questions. In the second half, I'm actually going to go into how to make an animated GIF using diagrams. It's really easy, but it'll give us an opportunity to kind of create another fun example. And I'm also going to talk about some of the design decisions we had to make. In particular, I'm going to talk about arrows, and then by arrows, I don't mean the categorical arrow. I just mean connecting, point A to point B. It seems like it should be the easiest thing in the world if you have a scalable vector graphics library to make arrows, but due to some of our design choices previously, like putting things next to each other and not really always doing things by connecting points, by not specifying the size of the diagram until after the fact, it actually becomes quite tricky. And so I want to kind of show you that as a kind of lead into some of the more interesting types in diagrams and how we actually handle that problem. So why don't we take let's say a 15-minute break and reconvene at 8:10.